Start the video. Um, so y- you probably know somewhat about nuclear reactions and processes. A lot of them are related in the medical field that you've seen, and and a lot of applications are in power and bombs and things like that. So we start off by looking at some of the applications, and as far as the medical applications go for nuclear chemistry applications, we have two different areas. One in detection of disease, and that's what uh, is addressed here in this first little bit of information. Uh, so nuclear decay gives off particles, as we'll see. And one of the particles that it gives off is light. So if you have uh, a atom that gives this particular energy off in the form of light, then you can imagine that if it's ingested into a biological organism, that you can follow it as it flows through the body. And this could point to maybe dysfunction if you compare it to someone who is healthy and someone who's not. So it can literally shed light on any medical problems from the inside. Uh, and so that's in the category of detecting um, illness in biological organisms, or things that aren't working properly. And then it can also be used in treating certain illnesses like chemotherapy and cancer, which I'm sure you've heard of. All right, so a little history of radioactivity. It's kind of interesting. It was discovered by mistake. Becquerel reportedly was um, one of those Renaissance scientists who was into a lot of different things, and he was taking rock samples, which he put into his dark room in a drawer next to some photographic plates, uh, and later discovered that the photographic plates were exposed, uh, but he didn't figure it out until after that it was the rocks. And he found that there was uranium in those rocks, so he called it uranic rays. But that wasn't quite right. And we find that out later. But the thing was that it was different from, say, phosphorescence, which is a property where you take a compound and you expose it to an energy source like light, and then you take the energy source away, and then it glows. It re-emits the light. Essentially, it's a forbidden electronic transition, and you've studied electronic transitions in Chem 200 for atoms. When they're in an excited state, they give off energy. Electrons jump from higher energy states to lower energy states, and they give off energy in the form of light. This is uh, kind of what phosphorescence is. All right, so Mary Curie, she was the one to, figure out that other atoms also were radioactive, not just uranium. And so that phrase uranic rays um, was not really appropriate. Um, but anyway, Mary Curie, she discovered radium and polonium, these two other radioactive elements that she named, and she coined the phrase radioactivity. So that replaced uranic rays, because other atoms have been known to have radioactivity. All right. This plate here tries to compare something that you know as far as chemistry, or should know, uh, compared to nuclear reactions. So we have chemical reactions on the left, nuclear reactions on the right. So we know that for chemical reactions, that bonds are broken and formed. And we know that there's energies that are associated with that. But anyway, the nuclear reactions are different because they change the identity of elements, whereas regular chemical reactions, you rearrange the atoms, but there's still the same number of that particular type. The energies that are given off or taken with chemical reactions, like the exo or endothermicity, are much smaller in general than the amounts of energy associated with nuclear reactions. So, millions of times in difference. And lastly, we studied the rates of chemical reactions when we first started the class, and we saw that rates of reactions depended on many things, like surface area, concentration, temperature, and so forth. But we find that the rates of nuclear reactions really don't depend on very much at all, except the concentration. So we take a look at that some more in detail later on. But these are some of the general differences. Now, radioactivity was discovered by Becquerel, and Curie kind of figured out some of the details. But it wasn't until Rutherford discovered the different types of radioactivity based on their ionizing power. And that's the ability to knock out electrons. And that's also was used to detect these type of particles. So we want to keep track of the subatomic particles in nuclear reactions. So what is done is kind of a new formalism for representing elements in the periodic table. We have, again, the symbol of the element, but now instead of looking at the molar mass and the other things that you might see in the periodic table, we have this set up where we have something to the upper left side of the symbol called the mass number, which is a summation of the heavy particles in the nucleus. And then, of course, we have the atomic number here to the lower left, representing the number of protons. And so if I wanted to figure out, for example, the number of neutrons that are in this atom, then I only need to take A and subtract Z from it to find the number of neutrons. But essentially, that's how we keep track of these subatomic particles. And oftentimes, the electrons are ignored as far as calculating the mass. Even though they do have mass, they're relatively light compared to the heavy particles in the nucleus. All right, so here's an example of 3 different isotopes of hydrogen. Now, isotopes, you have to remember, are different than isomers. And we're going to take a look at some isomers in the last chapter. But isomers are different molecules, um, different compounds, but they have the same formula. They have the same makeup of atoms. Isotopes refer to the nucleus, and they also refer to a specific type of element. So hydrogen has isotopes, helium has isotopes, lithium has isotopes, and so forth. So the thing about isotopes is there's the same element, which means they have to have the same number of protons, right? Because if you change the number of protons, you change the element. So all isotopes have the same number of protons, but they vary in the number of neutrons in the nucleus. So we have a hydrogen here, which has one proton and one electron. And this type of hydrogen makes up 99.99% of all the hydrogen that you find naturally around the Earth. The other two that we have depicted here is deuterium and tritium. Deuterium has two heavy particles, one proton and one neutron, and tritium has two neutrons and one proton. And so this is an example of isotopes, and it also illustrates the definition of isotopes. Any questions? As always, if you have any questions, just shout it out. Or if you're interested in one thing or another, maybe we can go into some detail. All right. Now you're going to have to look at nuclear reactions. So we always have this chemistry formalism where something on the left of the arrow reacts to form something that's on the right of the arrow. So we're going to continue with this type of formalism and talk about nuclear reactions or nuclear equations. One of the things that you should note in this depiction of a uranium-238 decay is that the particles are conserved. So I have my mass number, or A, here, and I have Z, or the number of protons, here. And we'll notice that the particles that they create, thorium and helium, if I add up the Z's for them and I add up the A's, then you see that everything's conserved. So 238 plus 4 is 238, sorry, 234 plus 4 is 238, and 90 plus 2 is 92. So whenever you see these reactions, or you are asked to make up a reaction or a nuclear equation, you should make sure that all the particles are conserved. All right. Okay, so now we go back to Rutherford, and in his research lab, he discovered these different particles using their penetration power. So he found that beta rays, or his research group found that beta rays penetrated the most, then gamma, and then alpha was the last. I'm sorry, I got that wrong. The gamma rays penetrated furthest, then it was the beta, and then gamma rays are last. So we have these three different particles that are emitted during a nuclear disintegration or radioactivity. And if you take a radioactive material and say encase it in lead with a little hole and focus it through an electric field, then those different rays not only come out according to their penetration, but also they're deflected by the electric field. So you see that beta rays are deflected towards the positive plate. So that gave evidence that beta rays are negatively charged, whereas alpha bent towards the negative plate, and that was evidence that the alpha particles are positively charged, whereas gamma were not reflected by the electric field at all. So there was it was concluded that there's no charge for gamma. And as we'll see later on, that beta is nothing other than an electron. This is a beta particle. So if I use my my nuclear formalism, this has zero mass, and it doesn't have any protons. It's an electron. So this is another symbol that we use for the beta particle, or you may have seen something like that, beta -1, 0. The gamma rays, which doesn't have a charge, whereas electron has -1, the gamma rays are just found to be high energy light. And the alpha particle, which is positively charged, you'll notice that the inflection or the bending from the path is less for gamma than it is beta, and that gave evidence to the relative mass of the two particles. It turns out that the alpha particle is none other than a helium nucleus. So, oops, wrong way. So the helium nucleus has this symbol. So it's much more massive than an electron, and therefore that accounts for this smaller angle of deflection. But it is massive, and therefore its penetration is small relative to beta particles, and then light will penetrate through objects more than the others. All right, now we go to some types of radioactive decay. And this is important for analyzing, say, atoms that you have determined are radioactive. What's most likely their decay process? Well, before you can predict that, you have to know what decay processes are possible. So we have a few here in the second part that we're going to go over, and these are possible decay paths. Now, this first one, we have a neutron that decays into a proton and a beta particle, or an electron. Now, does anyone out there know the difference? It's kind of, I'm going back a little bit. What's the difference between a beta particle versus an electron in an atom? Does anybody know? The answer is where it came from. The electron in an atom is outside of the nucleus, and you can find it in shared bonds, like shared bonds. whereas the beta particle originated from the nucleus. So it's essentially it's a high energy electron that's usually ejected out of the atom itself. So that's the difference between a beta particle and a regular electron. But anyway, if you look at that first possible process where it's proposed that a neutron converts to a proton and a beta particle, right off the bat, as soon as you see that, you say, wow, I can take a nucleus, such as hydrogen, for example, and in theory, I can convert, it would have to be deuterium or tritium because they're the only ones that have neutrons. I can convert that neutron into a proton and change that hydrogen into helium. Now, that's just a simple example, but you can imagine that you can pick any isotope in the periodic table, and if it undergoes this type of process, you can move it to other elements across the periodic table and change it. So that's an interesting type of nuclear reaction. The second one exemplifies an annihilation. So whenever you have antiparticles meeting, so here I have the electron, and by the way, this is another way to represent just a beta particle. So you'll see this sometimes as a beta, or you'll see it as an E, and it means the same thing. So I have an electron, and this guy is a positron. So it has the same mass as the electron. It just has the opposite charge. And so when a particle, like an electron, meets its antiparticle, the positron, then they go up in a flash of light. And that's the symbol for the gamma particle that we talked about. So the gamma particle is light. It doesn't have any mass. And so that's represented by the 2 zeros. Any questions so far? All righty. Now check out this next possible decay or process. Here I have a proton that's converted into a neutron and a positron. So this is called positron or beta plus emission. Sometimes it's referred to as that. And this last one, again, I have a proton, this time reacting with an electron and forming a neutron. So this takes atoms and moves them from right to left on the periodic table. Whereas this process up here takes elements and moves them from left to right across the periodic table. All right. Here's some of the different qualities of the particles. So here I have the alpha particle, which is, remember, sometimes given this symbol, or this one. That's all the same. It's the alpha particle. Then I have the beta particle, which is sometimes given this symbol, or this one. And then I have the gamma particle, which is sometimes represented like that. So gamma is light. It doesn't have any charge and it doesn't have any mass, but it penetrates through objects uh, relatively a lot more than the others. So if you take a flashlight and you put it under your finger, you see that that light goes through your finger and it kind of lights up your fingernail red if you've ever checked that out. Light just penetrates material much further than massive things. Now, the things with mass here are the beta and the alpha. Beta particles are going to penetrate 100 times more because they're about 2,000 times less massive. So than an alpha particle. Now, alpha particles can be stopped by your skin. Skin's pretty tough. 3 millimeters for beta particles and 2 centimeters into your human tissue. And that's why you see the light in your nails when you put it up to like a flashlight. And we also know this is true as well for the nature of the radiation. And the ionizing power is something that's sometimes overlooked, but is most important when you want to look at these different types of decay and connect like a danger to them. Which one can harm a biological system would be one of the things to look at is a ionizing power. And you know what that means. It's just the power to knock out electrons. And so the ionizing power, the most dangerous is the alpha particle. And then it goes in that order. One of the stories I think your textbook might talk about is the tale of two agents. And you can look this up. They're KGB agents. One in 1957 was poisoned by a radioactive source that gave rise to beta particles, which is high energy electrons. And this guy, he survived that poisoning. In 2006, another KGB agent was poisoned with polonium, I believe, which is an alpha emitter. And when you ingest this, I mean, you know, alpha particles can't go through your skin because skin's pretty tough. But if you ingest it into your body, then it just pounds your organs with these massive alpha particles. And so this other guy in 2006, he met up, he was a defector, a KGB defector living in London, and he met up with some KGB agents and had tea. Well, they put this polonium in his tea, and I think he lived 2 weeks after that, and there was nothing they can do to save him. It was probably a horrible death with this type of poisoning. And so they're still up to these tricks. Those the Russians, they've recently poisoned another political. Well, you've probably seen it in the news. I'm not going to get into it. Okay, so that's enough on that topic. Now we get to the neutron to proton ratio, and this is an important thing to talk about because it leads to what's proposed as one of the strongest forces that we know, which is this nuclear force, this force that holds the nucleus together. Now, in the nucleus of an atom, you know, there's protons and neutrons. So what's the model for the protons and neutrons there? Well, the protons are massive and they're all the same charge. So we would expect just from a Coulombic interaction that the repulsion between these charged particles that are forced in such a small volume would be enormous. And you would imagine that the protons in a nucleus would be unstable. They should just fly apart away from each other. But the theory is that the neutron is there to help hold the nucleus together. It's kind of like the nuclear glue. So that leads to a discussion of how much or how many neutrons do you need to hold together so many protons? And that leads to this next slide where we have a plot of different atoms in more specifically the number of neutrons in the atom versus the number of protons. So we have neutrons versus protons. And these little like dots here that you see, that represents atoms. And this whole like asteroid belt, it kind of looks like an asteroid belt or whatever, that's called the belt of stability. So that's where atoms exist in nature, will be found on that belt of stability. For example, we have carbon 12 down here, tin 20, gold, and bismuth. And those arrows indicate where on the belt you might find those particular atoms. So you see that for carbon, way down here with small atoms, the ratio of protons to neutrons is about 1-to-1 when they're small. But as the atom size gets larger and larger, the stable type of that atoms needs a disproportionately more number of neutrons to hold the nucleus together. So it bends away from that 1-to-1 ratio, which was good for small atoms, but not good for larger ones. So you need more glue, in other words, to hold those protons together as you get more and more protons. Now, that's all good and well, and you can extract all that information from this plot, but there's more information that you could get from this plot. So far, we see that for stable nucleus, as they get larger, they're going to need more neutrons than they have protons to hold them together. Now, the most stable atoms in this belt of stability would be the ones right in the center. Okay. And then you have the upper part of the belt over here and the lower part of the belt down here. So if you can identify nuclei on the upper or the lower part of the belt, then you can say, oh, well, the guys down here are on the low side for numbers of protons, if they're on this side of the belt. And the atoms up on the upper side are on the high side for number of neutrons. So if an element is found to be close to the upper side of the belt, you would say that it might go through a decay where I convert a neutron into a proton. If it's found on the lower side of the belt, then you might say, oh, well, those types have too many protons. And so you would look for a proton converted to a neutron. Now, what we just looked at some possible decays, and for proton to neutron, we found two possibilities: a positron emission or an electron capture. Remember, we looked at those back here. Okay, so there's two ways to convert protons into neutrons. And there was one way to convert a neutron into a proton. So we're going to use those now to rationalize possible decay paths for certain nuclei that can be found on the upper part or the lower part of the belt of stability. Now, once you get to this up here, the last atom, the bismuth atom, it turns out that whenever you go larger on the periodic table than bismuth, let's see, what would that be? Polonium is the next one. All the elements after bismuth are not stable. They're just too massive. And all the ones larger than bismuth are predicted to undergo a large mass reduction, and the largest mass particle that can be ejected is an alpha particle. So anything larger than bismuth is predicted to be all unstable and undergo alpha decay. So there's a lot of stuff that you can extract from this this plot here. And here's the things that we said already. On the top of the belt, too many neutrons. We can have a neutron converted into a proton. If the atom's on the bottom side of the belt, then too many protons. And we can look at these two different decays where we convert protons into neutrons, get closer to that center line in the belt and more stable products. All righty. Yes, so this is a recap of what we just talked about. Now, sometimes when you look at very massive isotopes and their decay, they go through a series of decompositions and eject a series of particles and new atoms. When we look at that in its entirety, we sometimes refer that whole thing, we call that nuclear disintegrations or a radioactive series, and all of the atoms that are produced are called daughter atoms. So we start at the top of this radioactive series with a U-238 radioactive atom, and I see that it drops in mass number by 4 when it goes to thorium. So this must be an alpha decay. And then it converts neutrons to protons this way. So each one of these are beta decays. And then I have another alpha decay, another alpha, 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 a beta, 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 alpha, alpha, until I get to a stable form of lead. And then that ends the radioactive series or the process.
Professor,
yeah, go ahead.
what's alpha decay again, or what happens in alpha decay?
Oh, alpha decay is when a helium nuclei is kicked out from the nucleus of the radioactive material. So we represent it as an alpha particle with this formalism, or sometimes you'll see it like this. But essentially, the mass number is 4. in a helium nucleus because it has 2 protons and 2 neutrons. So if we're tracking the mass number over here, then it should go down by 4, which it does when it goes from uranium to, say, thorium. So that it decreases by 4, uh, and you can write it like that. So uranium 238 goes to thorium 234 plus helium. So that's the process there. And this is how we usually write it in chemistry.
Oh, okay. Thank you.
Sure. Okay. Uh, there's these so-called magic numbers for nuclei too. So if you're asked to predict whether this nuclei, this isotope of an element, is stable or not, one of the first things you can look at to see is if it has these magic numbers for the number of protons or the number of neutrons in the nucleus. In general, though, even numbers of protons and neutrons are more stable than odd numbers. So the magic numbers are always even for protons and neutrons. So now this gives you another way to predict which nuclei are more stable than other nuclei. Just look for evens. So if you had a question that says, which of the order these 3 nuclei in terms of stability, then you would pick the ones with even number of protons and neutrons as the most stable. And then next would come either odd number of protons or odd number of neutrons. And then lastly would come the least stable of the list. You would pick odd protons and odd number of neutrons. And we don't get into the reasons. We just call it magic because we haven't studied it. But it's similar to, the quantum theory of atoms, where we put electrons in the shells, and these correspond to stable shells, like we use the octet for electrons and so forth. But anyway, that's outside the scope of this class. If you took maybe a nuclear physics class, you would get into that. I've never done that, so I don't really know the details. Next thing we should probably talk about is that the radioactive decay is a first order process. And you know about kinetics, and you know about different order processes, that concentration depends on the rate. But now we're talking about not a rate of reaction, we're talking about a rate of decay. And the concentration that we're looking at is the concentration of the radioactive particles. So this rate equation here would be the rate of decay. This is found to equal some constant times the concentration of radioactive particles to the first power. It's the first order decay process. And you've studied 0th order and 2nd order as well, but this one is the first order. And sometimes instead of using the concentration of the radioactive particle in its place, we could use the activity, which represents that concentration. So if this sample has a certain activity and this other sample has a larger activity, then the one with the larger activity has a larger concentration of the radioactive particles. So activity is sometimes used in place of concentration. Now, what do you measure activity in terms of? One way to measure activity is with units of disintegrations per second. So that's what D over S is, disintegrations per second. And that's also that unit of measurements called the becquerel. So it's given that abbreviation sometimes. This is also related to the Curie, which is 3.7 times 10 to the 10th disintegrations per second. So it scales it up a lot. And K is the old rate constant that you're familiar with from kinetics. And N is the number of nuclei that's related sometimes to the activity. So anyway, if you recall from previously, our first order rate equation looked like this. T plus ln 0, right? You remember that from kinetics? Well, this is the same thing. This is the first order integrated rate law. But here we changed this to an N and an N. We subtract both of these, subtract this from both sides. And now I get this equation here. And so this is another form or another way to look at first order integrated rate law. And this is the familiar half-life for first order. Now, remember, first order half-life is independent of the amount of the thing that's is decaying. So it only depends on the rate constant of that particular process, and the rate constant depends on what the atom is that's decaying. So all atoms or elements that decay have an associated rate constant, and all decaying processes are first order. So we can use this to date things. But before we get to that, we're talking about half-lives again. This just reminds you what a half-life means. That means if I start out with a strontium 90 sample and say I have 10 grams of it, its half-life is always going to be the same time. And so here it has a half-life of 28.8 years. So in 28.8 years, this is years, it got cut off down here. I cut my sample from 10 grams in half to 5. And then in another 28.8 years, I cut it down to 2.5 and then 1.25. So it doesn't matter how much you have. It's all the half-life. That means the time to cut that sample in half is always the same, 28.8 years for this sample of strontium. Okay, now in this plate, I have depicted some naturally occurring isotopes and some synthetic isotopes. And the naturally occurring ones, like carbon-14 in the upper atmosphere, can be used, as you know, to date biological organisms because they ingest carbon and incorporate it into their structure. And then once they die, they stop eating and the time clock starts ticking. So they don't get a replenish of that carbon-14. So they can be used for biological organisms. If you want to date rocks, which are much older, you might use uranium. Synthetic isotopes also exist. So these isotopes are made, say, at the nuclear power plant, and then they're put into a truck and driven over to the hospital, and we can use these in medicine. These guys are used in medicine. This one here probably is not going to be used in medicine because it's an alpha emitter and that would do damage. So maybe power, that could go into power plants or bombs or something. All right. So in this plate, we talk about how radioactive carbon dating works. And so in general, the idea is that nitrogen in the upper atmosphere, our atmosphere is made up of 80% nitrogen, gets bombarded by high energy particles from the sun and things. Anyway, the nitrogen can capture a neutron and form carbon-14. So carbon-14 is formed in the upper atmosphere, and the assumption is that concentration of carbon, which goes into making CO2, is pretty much the same over years and years and years. Now that's not quite true, so some corrections need to be built in, but in general, it seems to be good. So now this CO2 filters down into our food. So animals either eat plants, which use the CO2, or those animals are eaten by other animals. And so the CO2 in their bodies is at a certain level. And like I said before, once those animals die, they stop ingesting new source of carbon-14. So the amount of carbon-14 starts to decrease. And we can tell how much time it's decreasing using that first order integrated rate law, because we know, let's write that. ln concentration at some time over the initial equals minus KT. Okay. We know what K is because we know that T1/2 equals 0.693 over K. So if we know the half-life of the radioactive species, which we do for carbon, it's 5,730 years. I can put that in the half-life. I can solve for K for carbon. If I take a sample from a newly deceased rat or, I don't know, plant, I can figure out the concentration of that carbon-14 and put it in here. That's the initial concentration. Then I can find the concentration of carbon-14 in that bone that someone dug up and put that value here, use that K, and then solve for the time that that bone has been decaying. And so I could do that. Now that'll work to a limit because every time it goes through a half-life, you're cutting the amount of carbon-14 in half. And then, time goes on, and there's just not enough. After 50,000 years, there's not enough carbon-14 to detect. So it has its limits. Anything that's older than 50,000 years can't be dated using this process. All right, so I think this just fills in some of the gaps in my explanation. You can read that. Non-radioactive decay. There's two nuclear processes, and this goes into non-radioactive decay. So you have some nuclei that are radioactive because they're either on the upper or the lower end of the belt of stability, or maybe they're beyond bismuth. And then you can have some of those nuclei that are on the edge of radioactivity, but by themselves, they're not radioactive. And that's what it's talking about, non-radioactive nuclear changes. You can induce them to either split apart, that's called fission, or come together and fuse with other nuclei and make larger nucleus called fusion. And so instead of going on and talking about this right now, I think I'll just end for the day and we'll finish this up tomorrow. I'm going to move that homework back for the next chapter, and we'll just take our time and glide into the ending of the class. So I'll hang out, see if there's any questions. If not, that's all I wanted to get through today. Okay.
Thank you.
Yeah, I'll have a good day, guys. I'll see you tomorrow, maybe.
Okay, thank you. Bye.
Bye-bye.